Semigroups and their representations, Lecture 14, Preston-Wagner Theorem. Let us start by recalling Cayley's theorem for groups. So theorem, let G be a group. Then the map, which sends an element A in G to the transformation L sub A of G, which is defined as a left multiplication with A. So this transformation sends an element x in G to the element Ax. So the map, which sends A to LA, is an injective homomorphism from the group G to the symmetric group S on the set G. In particular, corollary, any group is isomorphic to a subgroup of some symmetric group. And in this way, symmetric groups are universal. So here is a proof of the theorem. If we apply the left multiplication with AB to an element x, we will get ABx, and we can write this as A times B times x. So this is the same as the composition of the left multiplication with A after left multiplication with B applied to x. And this indeed shows that our map is a homomorphism from G to the symmetric group SG. Also, if the left multiplication with A is equal to the left multiplication with B, then A, which is LA applied to the identity element E, should be equal to LB applied to the identity element E, and that is equal to B. And this proves that our homomorphism is injective. And this completes the proof of Cayley's theorem for groups. Now we can generalize this easily to semigroups. Theorem, let S be a semigroup. Then the map, which sends an element A in S to the transformation L sub A, which is the left multiplication with A, and this is a transformation of the semigroup S upper 1, so of the monoid associated to S. So that's the map from S upper 1 to S upper 1, which sends an element x in S upper 1 to the element Ax. So this map is an injective homomorphism from S to the full transformation semigroup T on S upper 1. So in particular, as a corollary, any semigroup is isomorphic to a subsemigroup of some full transformation semigroup. So, and in this way, full transformation semigroups are universal. And the proof is exactly the same as in the case for groups. Remark, the appearance of S upper 1 and not of S in this theorem is important because the corresponding homomorphism for S might fail to be injective. We will always get a homomorphism to the full transformation semigroup. However, if S is a semigroup and not as a monoid, then this homomorphism might fail to be injective. So for example, if we take as S a non-singleton semigroup with 0 and with 0 multiplication. So now we can formulate the Preston-Wagner theorem, which is the main theorem for today's lecture. And the claim is as follows. Every inverse semigroup is isomorphic to an inverse subsemigroup of some symmetric inverse semigroup. So symmetric inverse semigroups have a similar universal property to the symmetric groups or to the full transformation semigroups. Any inverse semigroup is an inverse subsemigroup of some symmetric inverse semigroup. The usual reference for this statement are two papers by Wagner from 52 and 53, published in Russian, and also a paper by Preston from 54, which is called Representations of Inverse Semigroups. Note that a naive way to prove Preston-Wagner's theorem by mimicking the proof of Cayley's theorem will fail, because the left multiplication with an element A, so the transformation of an inverse semigroup given by a left multiplication with an element A, is in general not a bijection. So it will not go to the symmetric inverse semigroup on S. So in order to prove our theorem, we need to adjust or adapt the proof of Cayley's theorem. So we need to find some analog of the left multiplication operator for inverse semigroups, but we need to formulate it in some more clever way. So let S be an inverse semigroup and let A be an element of S. Recall that this means that for this A, there is a unique element denoted A to the power minus 1, or the inverse of A, such that A inverse A is equal to A, and A inverse A inverse is equal to A inverse. So let us now consider the usual transformation of left multiplication with A, denoted L sub A. So that's a map from S to S, which sends X to AX. Now, here is a lemma. For any pair of elements X and Y in A inverse times S, so as soon as X and Y are different, then AX is different from AY. Proof. So, by assumption X and Y are in A inverse times S. So let us assume that X is equal to A inverse U and Y is equal to A inverse V for some U and V in S. Necessarily U and V must be different because X and Y are different. So if AX is equal to AY, then A inverse U is equal to A inverse V, and then we can multiply with A inverse and we get that A inverse U, which is A inverse inverse U, should be equal to A inverse V, and this should be equal to A inverse V, and this contradicts our assumptions. So this contradiction proves our lemma. Now we can define what is known as Preston-Wagner representation. Let us denote by lambda A the restriction of the transformation of left multiplication with A from the whole set S to the set A inverse S. So to prove Preston-Wagner theorem, we will show three things. First of all, that lambda A is a bijection from A inverse S to AS. Note that we have already shown that lambda A is injective on the previous slide. Second thing, we will prove that the map from A to lambda A is a homomorphism from S to the symmetric inverse semigroup on S. And finally, we will prove that if A is different from B, then lambda A is different from lambda B as elements in the symmetric inverse semigroup on S. And then, of course, Preston-Wagner theorem follows by combining these three claims. And the map which sends A to this partial transformation lambda A of S is called the Preston-Wagner representation of S. So we will prove that the Preston-Wagner representation of S is an injective map, and in this way realizes S as an inverse subsemigroup of the symmetric inverse semigroup on S. So let's prove claim 1. So to prove claim 1, we only need to show that lambda A from A inverse S to AS is surjective, because we already proved that it is injective. So let AX be an element in AS. Then we can write AX as A inverse AX. And here we know that A inverse AX belongs to A inverse S. And that AX is A inverse AX is exactly lambda A applied to A inverse AX. So this shows that lambda A is surjective and hence bijective. So this proves claim 1. Now we can prove claim 2. So to prove claim 2, let A and B be two elements in S. We need to prove that lambda AB is equal to lambda A after lambda B. This means two things. First of all, we need to prove that lambda AB and lambda A after lambda B have the same domains, and that the two partial transformations coincide on this common domain. And the second claim is straightforward. If X is in the domain of both lambda AB and lambda A after lambda B, then lambda AB of X is ABX, and this is lambda A after lambda B of x. So this is the nice property of left multiplication. So in reality, the only thing which we need to prove is that lambda AB and lambda A after lambda B have the same domain. So by definition, the domain of lambda AB is AB inverse S, and this coincides to B inverse A inverse S. And the domain of lambda A after lambda B, we will denote it by Q. It consists of all elements B inverse U in B inverse S, such that B inverse U belongs to A inverse S. So, if B inverse A inverse V belongs to B inverse A inverse S, then we can consider B inverse A inverse V, and this is equal to B inverse A inverse A inverse V. Now here we have two idempotents, B inverse and A inverse A, and in any inverse semigroup, idempotents commute. So we can swap them and get an element A inverse A, B inverse A inverse V, and this element is manifestly an element in A inverse S. So this means that B inverse A inverse S belongs to Q. So we have proved inclusion in one direction. Conversely, if we have an element B inverse U in B inverse S, and assume that B inverse U is equal to A inverse V for some V. So applying B, we get into A inverse S. Then B inverse U is equal to B inverse inverse U. Then B inverse U can be rewritten as A inverse V, and we get an element of the form B inverse A inverse V, and that's an element in the domain of lambda AB. So Q is a subset of the domain of lambda AB. So we have inclusions in both directions, so the two domains coincide. And this completes the proof. And finally, we can prove claim 3. Assume that lambda A is equal to lambda B. This in particular means that the domains of lambda A and lambda B coincide, that is, A inverse S is equal to B inverse S. So if we apply the inverse, we get that SA is equal to SB. In other words, A and B are left equivalent. Also, the codomains of lambda A and lambda B coincide. This means that AS is equal to BS, or alternatively that A is right equivalent to B. So A and B are both left and right equivalent, and so they are H equivalent. Now we can consider the right cell of A inverse, and it's the same as the right cell of B inverse, and we let E to be the unique idempotent of this right cell. Then we can write E as A inverse A or as B inverse B, but then lambda A applied to E is equal to A times A inverse A, which is A. And at the same time, lambda B applied to E is equal to B inverse B, which is B. And hence, lambda A is different from lambda B if A is different from B. Or alternatively, if lambda A is equal to lambda B, then A should be equal to B. This completes the proof of claim 3. Here is an example. Consider the multiplicative semigroup S with elements 0 and 1. This is of course an inverse semigroup where the inverse of 1 is 1 and the inverse of 0 is 0. The element 1 is the identity element of this semigroup, and hence the domain and the codomain of lambda 1 coincide with the whole of S, and lambda 1 is the identity transformation of this domain. For the element 0, the right ideal generated by 0 in S coincides with 0, so the domain and the codomain of lambda sub 0 coincides with the element 0. And lambda 0 is the identity map on this singleton element. This means that we have the injective homomorphism from S to IS on S, which sends 1 to lambda 1 and 0 to lambda 0. In the second part of this lecture, we will describe transitive partial acts over the symmetric inverse semigroup ISN. So let's classify all such transitive partial acts. For this, let us recall that left cells in ISN are indexed by domains, that is, by subsets X of the set 1, 2, and so on up to n, which we denote by n underlined. So we fix such a subset X and consider the corresponding left cell Lx, which consists of all elements in ISN whose domain is X. Then the set this left cell Lx has the natural structure of a partial act over our symmetric inverse semigroup ISN, and this is defined as follows. If we have an element sigma in ISN, then an element xi in Lx belongs to the domain of sigma acting on Lx, if and only if the composition of sigma after xi belongs to Lx, and if this condition is satisfied, that sigma acts on xi and outputs sigma after xi. The cell Lx contains a unique idempotent epsilon x, and this is the identity map on X. The domain of this element is X. And the H class of this idempotent is a group which is isomorphic to the symmetric group on X. Proposition: for any element xi in the H class of the idempotent epsilon x, there is a unique act endomorphism, in fact it will be an automorphism, of Lx that sends the idempotent epsilon x to xi, and we denote this endomorphism by f sub xi. Moreover, any act endomorphism of Lx equals to f sub xi for some xi in the H class of epsilon x. In particular, all endomorphisms of Lx form a group which is isomorphic to the symmetric group on X. Proof. This should be proof. Let us prove this proposition. So we know that sigma applied to epsilon x is equal to sigma after epsilon x and is equal to sigma for any element sigma in Lx. Therefore, any endomorphism of Lx is uniquely determined by its value on epsilon x, since all other elements of the act can be obtained from epsilon x by acting on it by some element in Lx. Note that epsilon x, when it acts on epsilon x, gives us epsilon x squared, which is epsilon x because that's an idempotent. Consequently, if f from Lx to Lx is a homomorphism of acts, then epsilon x acting on f of epsilon x is equal to f of epsilon x. But the set of all elements in Lx which have this property, so all elements xi such that epsilon x times xi is equal to xi, that is exactly the maximal subgroup which is the H class of epsilon x. And this means that any act endomorphism of Lx equals to f sub xi for some element xi in the H class of epsilon x. The fact that each f xi is an endomorphism follows as soon as we realize f xi as right multiplication with the element xi. And then the right multiplication with an element gives an endomorphism of an act, because the act structure is given by left multiplication, and of course left multiplication commutes with right multiplication. And right multiplication with elements in our group, the H class of epsilon x, of course gives a group which is isomorphic to the opposite of H epsilon x. So in particular, each f xi is an invertible element because we have a group, but of course any group is isomorphic to its opposite group via the map which sends an element to its inverse, and this completes the proof of our proposition. Now we can define quotients of cell acts. So pick now a subgroup K of our group H sub epsilon x. Then K acts on Lx by act automorphisms via right multiplication. That's what we discussed on the previous slides. Let Lx modulo K denote the set of all K orbits on Lx. Then this set inherits from Lx the natural structure of a partial ISN act. Since Lx is transitive, this partial act will also be transitive. And since the apex of Lx is the J-class which contains our idempotent epsilon x, so that's the J-class J sub epsilon x, the same J-class is the apex of our quotient x Lx modulo k. As a trivial example, if k is equal to the whole group H sub epsilon x, then the elements in the quotient act Lx modulo k are in the obvious bijection with the codomains of the elements in Lx. And these codomains are indexed by subsets of n underlined, which have the same cardinality as x. Now we can classify transitive partial ISN acts. So here is the formulation of the second main theorem. Let A be a transitive partial ISN act. Then there is M between 0 and n, and a subgroup K of the group H sub epsilon M underlined, such that A is isomorphic to the quotient act Lm underlined modulo K. Moreover, Lm underlined modulo K is isomorphic as an act to Lr underlined modulo K prime if and only if R is equal to M and K prime are conjugated in our group H sub epsilon M underlined. Let us note that here we stepped outside the previous setup. Instead of an abstract subset X of n underlined, we use a very concrete subset M underlined. So we fix one representative in the set of all subsets of cardinality M. This is enough for our purposes and it simplifies the formulation. Proof. Let A be a transitive partial ISN act. Then this act has an apex. This apex is a J-class, and J-classes are indexed by non-negative integers between 0 and n. So assume that the apex of A is the J-class, which contains the idempotent epsilon m underlined, where m is an integer between 0 and n. Then the idempotent epsilon m underlined acts as a non-trivial idempotent partial transformation of A. In particular, it has a fixed point on A. So let x be a fixed point of epsilon m underlined in our act A. Let B be the set of all elements y in A, for which there is an element sigma in Lm underlined, such that y is equal to sigma applied to x. Then, for alpha in ISN, we have that alpha applied to sigma applied to x is equal to alpha after sigma applied to x. And of course, alpha after sigma is either in Lm underlined, because sigma is in Lm underlined, or alpha after sigma belongs to a strictly smaller J-class, and hence it annihilates Lm underlined. So this means that our set B, which definitely contains x, is a non-empty ISN invariant subset of A. Hence it must coincide with A due to the transitivity of the later act. Now, if we send an element sigma in Lm underlined to the outcome of sigma acting on x, this defines a homomorphism, which we denote by phi, from the act Lm underlined to A. And this homomorphism is surjective by the previous slide. So let K be the stabilizer of x in our H class of epsilon m underlined. Note that the right H epsilon m underlined act L is free with a basis given by any cross-section of the right equivalence classes inside our left cell act. Therefore, our left cell act is also free as a right K act. And as a consequence, it follows that our act homomorphism phi factors through the quotient act of Lm underlined modulo K. So we denote by phi overline the corresponding homomorphism of acts from our quotient act to A. Then, directly from our discussion, we see that phi overlined is surjective. Let x and y be two different subsets of an underlined of cardinality M. Then the intersection of x and y has strictly smaller cardinality, which means that the composition of epsilon x and epsilon y is strictly j smaller than the j class which contains epsilon m underlined. Therefore, this composition annihilates A. We define A sub x as a set of all elements epsilon x times u, where u ranges through the domain of epsilon x acting on A. Then the above applies that the intersection of ax and ay is empty if x and y are different. And also A is a union of all axes. So to prove the injectivity of phi overlined, it is enough to show that all ax have the same cardinality. By construction, for the quotient act Lm underlined modulo k, the corresponding set which is indexed by x, if we go through all different x's, all these sets have the same cardinality. And this means that since the map from Lm underlined modulo k sub x to ax is surjective, and for the particular x equal to m underlined it is bijective, this means that the cardinality of ax is less than or equal to the cardinality of am underlined for any x. But of course, if we fix x, then we can do exactly the same arguments for x as we did on the first 3 slides of the proof. So we can substitute epsilon m underlined for epsilon x and h epsilon m underlined for h epsilon x. And then this will imply that the cardinality of ax is greater than or equal to the cardinality of ay for any y. Put together, we get that all a sub x have the same cardinality, and this implies that phi overlined is, in fact, an isomorphism. And this completes the proof of the first part of the theorem. In the last part of the theorem, we need to compare when Lm underlined modulo k can be isomorphic to Lr underlined modulo k prime. So if they are isomorphic, then M should be equal to R, because the apex of the former act is a j class of epsilon m underlined, while the apex of the later act is a j class of epsilon r underlined. Okay, so M is equal to R, and now let phi be an isomorphism of x from Lm underlined modulo k to Lm underlined modulo k prime. So this isomorphism induces a bijection from the set Lm underlined modulo k sub m underlined to the set Lm underlined modulo k prime sub m underlined. Both these sets are transitive acts for the group H sub epsilon m underlined, and from our classification of transitive acts over groups, it follows that K and K prime are conjugated subgroups in our group H sub epsilon m underlined. And the opposite direction is an obvious exercise. This completes the proof. Some additional problems and questions at the end. Problem question 1. Check with all details that if S is non-singleton semigroup with 0 and with 0 multiplication, then the homomorphism which sends an element A in S to left multiplication with A as a transformation of S is not injective. Problem question 2. Construct with all details the Preston-Wagner representation for IS2. Problem question 3. Write down all the details about realization of the endomorphism f sub xi of Lx via the right multiplication with xi. Problem question 4. Check with all details that sending an element sigma in Lm underlined to sigma applied to X defines a homomorphism of X from Lm underlined to A. Problem question 5. Prove with all details that if k and k prime are conjugated in H sub epsilon m underlined, then the partial ISN acts Lm underlined modulo k and Lm underlined modulo k prime are isomorphic. Thank you very much and see you next time.